Alright, so this lecture will be covering an introduction to functions, and then we'll go into modeling functions. So, quick definition, what is a function? It's a relationship between two sets of numbers or other mathematical objects where each member of the first set, which is the independent variable, is paired with only one member of the second set, which is the dependent variable. So, that was the formal definition. What I'm going to do is go ahead and explain a function by giving an example, a real world example. So here's an example. Let's look at a grocery store. Let's call this the RB grocery store. Alright, so you go into the grocery store to buy a few of your items. I'm going to make a table, and one column will have the item that you purchase, and after the register scans it, or the cashier scans it, the output is the price. So the input will be the item, the output will be the price. So these words are important: input and output for a function. Alright, so the first item may be, let's say, I don't know what sizes they actually have, but I'll just call it a gallon of the Simply lemonade. Alright, so if I take that to the register, the cashier scans it, and the output from the cash register is about $4.50. Let's say the next item is a whole pineapple. Pineapples are good. So they scan that into their register. The input is a pineapple. The output is about $2 for a pineapple. And then no particular brand, but I'll just say, let's say a dozen eggs. Right? The input is the dozen of eggs for some specific company that grocery store sells, and then the output will be $3.25. So in each of these, there's the input, the grocery store item, and then there's the output, the price. For each of these inputs, there's a specific output, right? For each of these inputs, there's a specific output. Here, what we're looking at is a real-world example of a function. This grocery store example represents a function. And a lot of times when I'm doing examples or working through problems where the problem will ask me if a certain situation is a function or not, right? Whether we're mapping, whether we're using a table, whether we're using ordered pairs. When it's asking me if a relation is a function, I go by this grocery store example and I tell myself, okay, for each of these inputs I have an output, therefore this is a function. If I were to add something extra, right, let's say I do this, maybe add another pineapple, the exact same brand of pineapple, same weight, everything, right? So I add that other pineapple, but then the output says $5. Well, we know that can't be right because all of the inputs must have the same output. So that's the definition of a function. You can't break that rule. Each of these inputs, if the inputs are the same, they have to have the same outputs. Here it doesn't. So this breaks the rule of being a function. So that cannot occur. So let's erase that. And looking at what else could happen. Let's see. Maybe we get a bag of apples. We input that into the register scanner, and then the output is $2. Now that could very well happen. Two different items in a grocery store could, in fact, maybe end up being the same price. And in this case, they did. So, in this case, two different inputs can have the same output. The pineapple can be $2 and the bag of apples can be $2. However, going back to the previous situation, the same input cannot have two different outputs. All right, so understand that from a grocery store example, you'll be able to apply this to what we see later on in different examples. All right, so this was my example of a function. All right, so next, let's go ahead and take a look at a real-world example. And what I want to look at is a swimming pool. So if we have a swimming pool and the swimming pool is filled up with water and we're emptying the swimming pool. Okay, so let's say this person, Al has a pool and that pool is filled maybe to a certain depth. So we'll call it a depth of 80 centimeters of water. All right, so his pool is filled to a depth of 80 centimeters of water. All right, now he's emptying the pool out. He had a long day of friends there, and now he has to empty it out, then start cleaning it and stuff like that. So he is emptying the pool at a rate of, let's say, about 12 centimeters per minute. 12 centimeters per minute. All right, so the pool starts out at a depth of 80 centimeters of water. So he begins emptying the pool at a rate of 12 centimeters per minute. So what we want to do is write an expression to represent this situation, right? Write an expression that represents this situation. So we can rewrite this as a two-variable situation, right? If we wanted to have y be one variable and x be another variable. The x can represent time if we choose, and the y could represent the water level in the pool. So we can in fact write something such as this: y is the water level of the pool, right? So y is equal to, well, we said that it started out at a depth of 80. So it starts at 80. That's the beginning water level, 80 centimeters. But we're emptying the pool, or Al is emptying the pool. So it must be subtraction, right? If he were adding water, then we would say addition. But he's emptying water, taking water away, taking water out. So it's subtraction. But then he's emptying at a rate of 12 centimeters per minute. So 12, and I had mentioned that the x can be the time in minutes, so 12 centimeters per minute. All right, so take a look at that and see if that makes sense to you, where again the y represents the water level in the pool. So y equals the water level in the pool, right? And the x is going to be in minutes. Since he's emptying the pool in minutes, x represents the time. All right, so I'll put time in minutes. So see how that makes sense. Y, the water level, is equal to 80. It starts out with 80 minus, because it's being emptied, at a rate of 12 centimeters per minute. So 12 is what they gave us, centimeters each minute, and x stands for the number of minutes. We don't know how many minutes, so we're using that variable. All right. We can even rewrite this. Instead of writing y, we'll use f of x. F of x is equal to 80 minus 12x. So f of x can represent the y. This f of x is the output, where that x is our input, or any x that you see is the input, right? So the X is the input, the Y is the output. So if we plugged in something for X, a number of minutes, we can see how much water is left in the pool. So if we plug in the minutes, we can see, do the calculations and see how much water is left within the pool. So we had written this as a two variable problem, and now we rewrote it using function notation. Function notation. So be sure to understand that this is a multiplication. It's not f times x. It's function notation. In function notation, we read this a certain way. We say f of x. And in other problems, you'll see they'll use g of x or h of x, or maybe if it's an applied problem, a business problem, they may use p of x for profit, or they may use a problem like h of x for height, or something like that, just to represent whatever they're talking about. But usually in a math problem, they'll use f of x, g of x, h of x, and then from this point on, you'll understand this as function notation, and that f of x really represents y, really represents y. So let's go ahead and look at the function notation. So let's say f of x is equal to 80 minus 12x. So we've just modeled this situation as a function, this emptying of the swimming pool. So let's say we would like to find the depth in 1 minute. So find the depth of the water in the pool in 1 minute. So basically, what are they saying to find? Find f of 1, right? Because 1 is that input, and our output will be the depth, f of x. So everywhere we see an x, we're going to substitute in a 1, right? So we have 80 minus 12 times 1 is 12. So 80 minus 12 is 68. So f of 1 is equal to 68. So what does f of 1 or f of x represent? It represents y. And so we said the y was the depth. So the depth of the water is 68, and I believe we were talking in centimeters. So centimeters. So the pool began at 80 centimeters. However, after 1 minute expired, the depth of the pool is 68 centimeters. And we could do this for different x inputs, right? We could do it for 3 minutes and see how much water we have left. We could do it for 10 minutes and see how much water we have left. In fact, let's go ahead and do it. Let's find f of 3. What does that mean? That's saying to find the depth of the water in 3 minutes. Find the depth of the water in 3 minutes. So f of 3 is equal to 80 minus 12x. So everywhere we see an x, we're going to input a 3. So 80 minus 12 times 3. All right, f of 3 is equal to 80 minus 36. And then we're just going to go ahead and subtract. So 80 minus 36 is 44. So the depth after 3 minutes is 44 centimeters. All right. And then lastly, let's do one more. This one says find the depth in, let's say, 10 minutes. The depth of the water in 10 minutes. So we're finding f of 10. F of 10. All right. So everywhere we see the x, we're going to plug in that 10. So we have 80 minus 12 times 10. And then we have 80 minus 12 times 10 gives us 120. So now it looks like we're going to get negative 40. All right, what is this saying? This is saying that after 10 minutes has gone by, the water started out at 80 centimeters. 80 centimeters. After 10 minutes has gone by, then the depth of the water in the pool is negative 40. Well, how can that be, right? That can't be. We can't have negative 40 centimeters as a answer, right? There's no such thing. So what is this saying? This is saying that at a certain time, we're not sure which time yet, but maybe somewhere between 3 and 10. I know it's not 3 because we said 3 was 44 centimeters. Somewhere between 3 and 10 or something like that, the pool ran out completely of water. And then the mathematical model we have here keeps calculating. The model doesn't know that, right? So it just keeps calculating and calculating, and it does the math and it says negative 40. The next thing we're going to do is make a table showing the first 5 minutes. So we already calculated the first minute together. So we need to write this as ordered pairs. And I'm using Desmos.com. And Desmos.com is a great tool. It has an online graphing calculator. And I'm going to use this to make the table as well as graph the first 5 minutes of our function. So I think we said that during the first minute, that was the input, the first minute, right? That X variable. We did the calculation and came out with Y being equal to 68 centimeters. So we typed that in as an ordered pair, parentheses 1 comma 68 close parentheses. All right. And I've already done these on the side, and you can work through them on your own as far as getting the minutes. We did the first minute and we did the third minute. I did 2, 4, and 5 on my own. So let me type that in. After 2 minutes, the pool is at 56 centimeters. After 3 minutes, the pool is at 44 centimeters. And after 4 minutes, the pool is at 32 centimeters. And after 5 minutes, the water level is at 20 centimeters. All right. So let's go ahead and take a look at how this is going to look for us. If you don't see it, sometimes you may have to zoom out, right? Because we're at numbers like 68, 56, 44 and such on the y-axis, where we have smaller numbers on the x-axis. So there it is. So I'll zoom out again a little bit, and then I see it right there. And I've graphed the ordered pairs. So you could do this by hand if you chose to. If you got yourself some graph paper, make an XY coordinate system and then just plotted these points. Or you could use a graphing calculator or even something like I'm doing on Desmos.com. Alright, so we've graphed the ordered pairs from the table. Alright, so let's take a look at how it looks. If we were to draw a line through all of these, it's a straight line. It's a straight line. And the line goes all the way through forever and ever and ever, if we wanted to. And it will cross the y-axis up here somewhere and cross the x-axis down here somewhere. Alright, so I've exported the Desmos graph back to my OneNote so that we could go ahead and explore a little bit further. So again, our situation was taking a look at the first 5 minutes in the emptying of water from this swimming pool that started at 80 centimeters. So in the first minute, the water level went down to 68 centimeters. In the second minute, in orange, the water level went down to 56 centimeters. In the third minute, which is represented by the green dot, it went down to 44 centimeters. And then the purple dot is 4,32, so that means after the fourth minute, it's at 32 centimeters. And the black dot is the order pair 5,20. So that's telling us that after 5 minutes, it's down to 20 centimeters. So what I'm going to do is just use this specific situation, and I'm going to relate this graph and our situation to these terms to the right, and I'm just going to relate it specifically to our situation. So as far as an intercept, if I were to go ahead and connect these dots, our graph doesn't go on forever due to our situation. We only were concerned about the first 5 minutes. Um, the x-intercept is where the graph or your graph touches or crosses the x-axis. Well, obviously you don't see the line extending because we only did the first 5 minutes. Maybe if we did a few more, it would. So there is no x-intercept. So there is no x-intercept for us, right? If we were to extend it some more and do a few more minutes and do a few more calculations, maybe then it would go and cross somewhere right here, and we would name that ordered pair the x-intercept, whatever it was. Now we're looking for a y-intercept. So don't let this fool you. Again, the y-intercept is where it touches or crosses the y-axis. It looks as though it's touching, but that's only because I had to zoom out. If we were to zoom in really closely, and if you were to do that on Desmos, you would see that this ordered pair is 1, 68. 1 is the x, so it'll be here at the 1 tick mark. It's not quite on the axis as it may seem right here. So we have no y-intercept. It's not touching or crossing the y-axis at all either. If we were to extend it some more or start it at point 0, then we would see that the y-intercept would actually be at 0, 80, right? Because it starts out at 80 centimeters. So that's what the y would be, the level of water in the pool, right? Makes sense? 80 centimeters. But for our situation, we did minute 1 through 5. So there's no x-intercept, no y-intercept. The domain are all of your inputs, and I told you vocabulary is important. The domain are all of your inputs, your x variables. So the domains are 1, 2, 3, 4, and 5, right? So 1, 2, 3, 4, and 5 is your domain. Those are all the inputs, the x values. The range are your outputs, your y values. Again, the range will be your outputs, your y values. So our y values were 20 centimeters, 32, 44, 56, and 68 centimeters. So we have our domain and range. All right. Now we need to look at independent variables and dependent variables. Well, it's just what it says. An independent variable stands on its own. A dependent variable is dependent upon the other variable. A dependent variable is dependent upon the other variable. So let's take a look at our situation. One variable was the y, which is the depth of the water. Another variable was the x, the minutes that have elapsed if we were emptying the pool, right? It's like if the pool was punched in the side with a pin or a nail, then after a certain amount of minutes, more and more water would empty out of the pool. So this is like our situation. So I'm thinking that the level of water in the pool, the depth of water in the pool, depends on how many minutes elapses. Doesn't that make sense? The level of water in the pool, how much water the pool has, is dependent upon how much time has elapsed, how many minutes have gone away. So therefore, our y is the dependent variable, right? And our x was the independent variable. So the y, the depth of the water, is dependent, and the independent is the time in minutes for us. So we have an independent variable and a dependent variable. And in dealing with functions, your x variable will always be the independent variable, and your y variable will always be the dependent variable. So as you can see, the concept of function is best understood in terms of a real-life situation. For example, at any single point in time, Al's pool can only have one depth. But if we were to look at this backwards a bit, the pool could be at about 80 centimeters at many different points in time, right? Because he could always refill the pool. So there we have it, an introduction of functions and modeling functions. If this helped you out in any way, please be sure to hit the like button. Feel free to share with friends, family members, or other classmates. And don't forget to subscribe to the channel. Have a great one.